All right, guys. Well, welcome to the third workshop. And today we will be covering 2D DP. And in the previous workshop, you probably learned from San one-dimensional DP. And 2D DP is just the logical extension of that. And it will allow you to solve, a variety of extra problems. And it's fairly common in competitive programming. So it's good to have the fundamentals down with regards to that. So also when it comes to 2D DP, so two-dimensional dynamic programming, it will also feature kind of heavily when it comes to graph theory, which will be the next and final workshop for today. And that's because graph theory also requires some memoization, and it also needs 2D arrays or like 2D lists. So throughout, I'm going to be mentioning 2D arrays or 2D lists. And these two terms, for us at least, are interchangeable. And basically that just means in Python, when I have one list inside of a bigger list, right? And right now we're just going to cover some basic structure. Okay, so as you can see, this is an example of a 2D list. You have DP equal to, this list. Well, this isn't exactly an example of a 2D list, right? Because it's actually got several lists inside of one another. So this example, it just kind of is supposed to show you like the flexibility of a Python list. In other languages like C++, you won't be able to do something like this. You won't be able to put all kinds of different variable or data types in one single list, because here you have like an integer, strings, a Boolean, and then another list, right? So in Python, you're able to do this. In other languages, you aren't. And yeah, if you put this code like into your Python program or something like that, and you print, the output should give you 2. And the reason for this, right, is because of these indexes. So the first index, the 2 here, it tells you which one of the lists inside the biggest list to access. So inside the biggest list, there is this, then there's this, and then finally, there's this, right? So there are 3 elements inside the biggest list. And when you do DP at index of 2, you access the final list at index 2. Now, once you're there, the second indexing, or like the 4 inside those brackets, it tells you which element to access inside this smaller list. And as you can see here, in the smaller list, there is 5. There are 5 elements. And by putting in that 4, you access the element at index 4, and that would be this final smallest list, which has the numbers 1, 2, 3. And if you access the one at index number 1, you get number 2. Now, throughout here, you have to remember that with a list in Python, the indexes start at 0, no matter if it's the biggest list, the list inside of that, or the list inside the, other list, or like the smallest list. No matter what, all lists start with index 0. So yeah, that explains why you would be getting the number 2. Now, generally, when it comes to 2D lists in Python, you'll be creating ones that are rectangular. So the one that I have over here, that is not rectangular. Now, I will go into what rectangular means. So by my definition, at least, right, rectangular is when you have a 2D list that has like the lists inside the biggest list are all the same length. And yeah, that's my definition of rectangular. Now, the reason why I call it rectangular will become apparent later. I'll also go over some other terminology that I like to use. So I like to call like the biggest list the prime list, or the primary list. So this biggest list that holds all the other lists and all the other elements inside, I would call that the prime list, right? Or the primary list. So that means that it's the biggest one. All the other things are inside of that. And then a list like this, I would call the secondary list because it is inside the primary list and it is smaller than the primary list. Well, it is inside of it. Smaller, bigger doesn't really make sense here because you can have, like this list could have like 100 elements inside, right? And the primary list can only have like, 3 elements or 3 lists inside. So bigger or smaller isn't very accurate here. Like nested inside of or outside of, that's the terminology that works. Okay, yeah, thank you, Gordon, for providing the check-in code. All right, well, we will go on down. So yeah, as you can see here, and this will be made available to you after the lesson is done. So yeah, as you can see, there's my definition of what rectangular means. And here is a way of creating a rectangular list. So you can copy and paste that into your programs and run it to see what it does. And I'll do that on my side as well. All right, so I will copy and paste that. I'll go into my replit. So the thing that I have here, it's all commented, so it won't affect the code running. This is a problem statement for something that we'll do later. You can ignore this for now. So to show that, I'm just going to indent a bunch. So no need to pay attention to that kind of stuff. So yeah, we're just going to run this code here. And if we run it, that's what it prints out, right? Very messy looking, right? But if you look at it, you have placeholder being 0. You have x being equal to 10, y being equal to 12, right? So this is the important thing to pay attention to here. So ARR is the variable that will be holding our 2D list, and you are creating it, and you're making it set equal to this thing over here. Now, this is an example of list comprehension. It's basically when you kind of shorten a nested for loop and put it all on one line. And this is useful because it saves space in the program. And especially in competitive programming, sometimes like when you submit your answer matters. So if you can save time and like write a piece of code that's easier to type out, then definitely that's a good thing because it could be the difference between you getting a good score or like maybe a less good score. So yeah, I'll just quickly explain this. So usually it's a good idea to like proceed from these things from the inside out. So we'll start with the secondary list, which is starting from here, ending from here, right? Now you have placeholder and then for k in range x. So, like all for loops, you're going through x iterations because you're doing for k in range x. So that means that you'll be doing something 10 times. Now the question is, what are you going to be doing 10 times? Well, you're going to be doing something involving placeholder. Now we know that placeholder is equal to 0. And in the output, we see that there's a bunch of zeros. So most likely what's going on here is that you're creating multiple copies of placeholder. And if we pay attention to the output here, you can see that in this secondary list, there are actually 10 zeros. So that's the explanation for the secondary list here. You are creating 10 zeros because you're going through 10 iterations. In this case, x is equal to 10. So you're going through x iterations and you're putting a placeholder into the secondary list for every single one of these iterations. Now, I could have set placeholder to be any number. I could have even set it equal to a string like hello. Now, this is going to be even messier, but it goes to show, right? You're placing 10 hellos in the secondary list, which is the smaller list that is inside the primary list, which is the biggest list. So yeah, now that we have the secondary list explained, we just have to cover, I guess, everything inside the primary list. Now, if you look at it, this is almost like when you nest functions. If you guys, in math nest functions inside of each other, this is exactly like that, where the format's kind of the same, right? Because here inside the secondary list, we have placeholder and then for k in range x. And then inside the primary list, we have, yeah, sure, the secondary list, but that for j in range y. So it's following the same kind of, variable for, iterator in range, certain number. It's following that format. And what this means, or what this does, is it will create y, it will create like y instances of the secondary list. And with that, you've created your 2D list. So let's change this back to 0 so things are a bit more clear. And let's also decrease these numbers. We don't need them to be that high. So we can make this maybe like 5, make this 6, and we run that. Yeah, it's a bit more manageable. And you can see that there are actually going to be 6 secondary lists inside the primary list. And yeah, that's how list comprehension works. The first list that you type out is going to be coding for the size of your secondary list. And then the second part of it that you code out is going to be coding for how many of those secondary lists will be inside of the primary list. And that's how you do it. Now, it might be kind of like, it's not that difficult with 5 and 6 right here, right? You can easily count these, but even then it's kind of messy looking, and you might want a better way of looking at your code and checking it over, because throughout the implementation process, it's extremely important that you kind of know what's going on in your code. And if a bug happens, a great idea is to print a lot of things. And now you don't print random things, but what you want to do is when you're debugging, you want to see what your code is doing. And the only really real way to see what your code is doing is to make it print out what it's doing. So in this case, though, if you just print out the 2D list, it's in a bad format. So to improve that, you will need to use pprint. And pprint just stands for pretty print, and it will print it in a way that makes it easier for us to read. So you want to do import pprint. And then now this green squiggly line is just Repler reminding me that I'm not using pprint anywhere, but that's going to change. So I just do pprint.pprint, right? Now the reason why I have 2 pprints is the first pprint is telling me which like package I'm using. Since I imported pprint here, I need to specify that I'm going to be using the pprint package and using its pprint like I guess function. So now if we run it, oh yeah, okay. So sometimes Repler lags a bit. So this, after using pprint, you can see there's a whole world of difference, and now it's way easier to tell what your program is doing, and also to look at your 2D array. And this is the reason why I say most 2D arrays in dynamic programming will be rectangular. As you can see, it's in a rectangular shape. Its width is constant and its height is constant, or its length and width are both constant. Not constant, but like the point is that it looks like a rectangle kind of thing. And once again, you have 5 elements in the secondary list, 6 elements in the primary list. And if we want to make it a bit longer, change y equals to 10, because y is the number of secondary lists. And yeah, it's gotten longer. So I've defined it this way. When you actually do a dynamic programming problem, you don't need to do x equals 5, y equals to 10 to do that. You can usually just, write a number here, like 5, right? Instead of setting a variable to that. But I've only done that here just to show you guys, what goes into these ranges, and also like how, changing them affect the output overall. But when you're actually doing it, you can just skip the process of, x equals 5, y equals to 10, and you can just put those numbers in yourself. And yeah, same exact output. So someone in the chat. Yes, you can do from pprint import star. And yeah, in that case, if you do that, then you don't need to do pprint.pprint. So from pprint import star, and this just means import everything. And yeah, it works here. So yeah, in this case, you make the first line a bit longer and you shorten the second line. I don't know, like I just prefer my previous way, I guess, a bit, because sometimes it's good to like first of all, I don't like these green squiggly lines, and second of all, when you're using other methods like math, it's usually not a good idea to import everything from math, because the thing is, when you import a package, you get a bunch of, or like if you import star, or like if you import everything from a package, you get all the different functions and modules contained in that package. And sometimes you might be naming a variable, or you might be creating your own function, and you might inadvertently name it the same thing that was included in a package, and that can cause some weird issues in your code. So I usually like to not, like I usually like to play it safe, I guess. But in the case of pprint, usually I feel like it doesn't include too much more than just pprint itself. So you probably won't run into that kind of issue. Yeah. The shortness doesn't really matter here because like it's at most is a couple of characters. And to be honest, it's highly unlikely that you're gonna like, I don't know, lose a like a competitive programming uh place or like a spot because you had to type an extra character or two. But yeah, we can stick with this for now. So yeah, as you can see, it works. It's rectangular. I call it that because it looks like a rectangle. And yeah, let's move on. All right. So Python allows us to use negative and positive indexes or indices, but you just have to make sure that you don't go out of bounds, right? And this is something to pay attention to with 1D. This is something to pay attention to with 2D, or however many lists you're nesting inside of each other. Always pay attention to your indexes, because going out of bounds, that's going to make your code crash. Now, just as a refresher, positive indexes start at 0, -1 start with -1. And what I mean is, like, you're not gonna have, let's see, you're not going to have, so let's just print a certain thing in the array, right? I can print 0, 0, right? And that will give me 0. Yeah. Well, actually, all of them will give me 0. So that's kind of a bad idea. But you wouldn't do like -0, obviously, because 0 doesn't have a sign. So yeah, the positive ones or the non-negative ones start with 0, and the negative ones start with -1. So if I did -1, it would give me the very last, the bottom right-hand corner 0. Now I'm gonna change this up so you can actually tell the difference, because right now I could be printing whichever one of these zeros and you wouldn't know the difference. So yeah. Okay, yeah. So let's do some practice here. So we're gonna do this, and then we are going to pprint the array. Well, yeah, the 2D list. Going to do that, and I should probably make these numbers big again, just to make sure I don't go out of bounds. So yeah. And now you can see, and so yeah, pprint works if your 2D list is big enough, and it works pretty well. So as you can see here, if I do 0, 0 and set it equal to 1, that gives me the upper left-hand corner. And the reason why is, so this is the first secondary list in the primary list. This is the second, third, fourth, fifth, all the way down to the final secondary list inside the primary list. That can be kind of unintuitive, I guess, because as you increase the first index, you are kind of going lower and lower instead of going higher and higher. But as long as you keep in mind that usually it starts at the upper left-hand corner, then it shouldn't be too confusing. And then here, this piece of code makes me change the value of the bottom right-hand corner. And I'm setting this one to 1. And as you can see here, I have to use -1, -1. So what happens if I change this into, say, 4, right? Well, we can run the code, and we see that the 1 has shifted. So we do know that, this line corresponded originally to this. Now it corresponds to here. And yeah, you can mix and match like positivity, right? You can have a negative integer in the front, and you can have a positive integer following that, or you can have positive and then negative. And once again, this is index 0, index 1, 2, 3, 4. So yeah, it makes sense. And then finally, we can look at the placement of the 9. And once again, it shows us that the first index that we have tells us how far down to go. So it tells us to go to index number 4. So you just do that, vertically, you come over here, right? And then it tells us, the second index tells us how far to go to the right, and you go 7 to the right, or you move to index 7 on the right, and you have 9. And that's where we placed it. And if we were to change that number, it would change the placement. And yeah, a pretty good way to keep track of this is that the first number tells you how far down, how many like places down to go, and the second number tells you how many places to the right to go. So yeah, you go 4 down, so 1, 2, 3, 4, and then you go 7 to the right, 1, 2, 3, 4, 5, 6, 7. So yeah, that's one of the perks of having indexes start at 0 originally. And obviously 0, 0 means you stay at the upper left-hand corner and you just change that value there. All right. And yeah, here I was using the just the import pprint, but in the code we're using from pport import star, from pprint import star, and you can use either. All right, and now we're going to go over like the actual recognizing of examples. So what I did before was the basic structure, right? Because with 2D lists, you have to be comfortable with looking at, understanding, and also creating these 2D lists or 2D arrays, because that's what you're going to be using when you are coding. All right, there was something in the chat. All right, you don't have the run button. Like in your because in Replit you have the run button, but if you have like downloaded Python or like some kind of IDE, then you probably won't have the same loadout as me, and it might not be run, it might be like compile, it might be something like that. But if you are in Replit and you don't see the run thing, maybe reload it, because Replit, a lot of the times, it always seems to me that it gets like stuck or it gets laggy at the worst possible moments. Yeah, so with an idle, you will need yeah, F5. So yeah, good job everyone in the chat. Thank you for answering that question. Yeah, but it's definitely something F5. It might be Command F5, Control F5, maybe Function F5. But I haven't installed Python in this computer yet because it's kind of relatively new. So on my old one, I had a Mac and it was definitely like Function F5 or something like that. Okay, so let's move on to recognizing examples. So with 2D DP, the most important thing is to actually know when you are supposed to use 2D DP. And one way of doing that is to look for dimensions, right? Now, usually we think of dimensions as like, up, down, left, right, forward, backward, right? The Cartesian plane, there's like the 2D one, right, with the X and Y axis. There's the 3D one with the X, Y, and Z axis. And then, that's what we think dimensions are limited to. But I learned in my calculus and vectors class a couple of maybe weeks ago, I think, that dimensions aren't just limited to like these, domains of numbers. Instead, dimensions can mean all kinds of things. They can even mean qualitative things like color, right? Color can be a dimension. Size can be a dimension. Weight can be a dimension. All of these things aren't exactly three-dimensional or like, or they're not really things that you can put on a chart per se, but they are still dimensions. And at the end of the day, dimensions are kind of just like parameters, right? Things that you can put into a function or things that define an object. And the key with 2D DP is to look for something that has at least 2 dimensions. All right, so now we're going to be going over some of the examples of 2D DP. So in my lesson here, I've written that knapsack is a very common type of problem. So with knapsack, the problem is usually like, you have a bag and the bag can only hold like maybe 100 kilograms worth of weight before it breaks. And in front of you, you have like a bunch of different items, right? With varying, like, I guess, monetary value. Maybe you have like $100 block that weighs like 10 kilograms. Maybe you have a $1 block that weighs like 2 kilograms. and on and on and on, right? And the question of knapsack is, what's the maximum value that this sack can hold? Now, without 2D DP, this question is really long, really tedious. What you do is you have to like go through all the possible combinations and then see which combination gave you the best, like, or the highest monetary worth. And that's really slow, and you shouldn't do it that way. If you try and solve a problem that way in competitive programming, you'll probably time out, as in like your code will be too slow, or it will require too much memory and you won't be able to solve that problem. So with Knapsack, you will use DP, and especially the 2D version with this grid. Now, all 2D DP problems, involve a grid, hence why they're 2D. So I'm actually going to cover one of the more difficult varieties because I think that will be more interesting. And yeah, like Knapsack, it's more intuitive, so I think it's slightly less necessary to cover. But once again, the two dimensions here are the weight. Weight is a dimension after all, and the monetary value, or just whatever value. Sometimes it might even just be like sentimental value, right? But that is still another dimension. So weight and value are the two dimensions in this problem. And if you recognize that, you will be able to use 2D DP to find the maximum value in a shorter amount of time and using less memory. And then there are these problems that require you to figure out ways to reach a point. Now, this one is pretty common even outside of programming. Like if you do math, there might, okay, that's really random, if you do math, like obviously we all do math, but like certain math questions will give you like a grid, right? And they will ask you how many different ways to get from like the top left-hand corner to the bottom right-hand corner. And the key here is that the two dimensions are moving to the right and moving down. Those are the two dimensions. And in this case, the dimensions are actually, like kind of numbers related and related to like the normal Cartesian kind of grid or graph system. And then finally, finally here, I'll be talking about edit distance problems. Now, these, in my opinion, are some of the least intuitive, or at least for me, and I think will be very important for you guys to kind of look at this. And this is because like the solutions of a lot of these questions, they are very similar. Like Knapsack and edit distance problems, they have almost the exact same like layout. And it really surprised me. But yeah, there are only, I guess, so many ways to approach these problems. And so the good solutions will usually have something in common, especially in dynamic programming. So these edit distance problems, they involve being given a string and being tasked with changing said string into another one in the least number of moves required. So now we can finally go to our replit here. And that is the question. Oh, sorry. Yeah, that's the question. So given two strings, string 1 and string 2, and below operations that can be performed on string 1, find the minimum number of edits or operations required to convert string 1 into string 2. So you can either insert, remove, or replace. And all of the above operations are of equal cost. So what I mean is, say you have a string yang, right? And you have, say that is string 1, and you want to turn it into string code, right? Well, I mean, this example is not too interesting, but the point is you can insert, remove, or replace things to the string yang, and then you're trying to get the string code. Now, how do I change one to the other? Well, you could probably just replace every single letter in my name with C and then O and then D and then E, because my name shares nothing with code. So that is not very interesting. If I did sang, right, not only does it rhyme, my name shares 3 letters with it. So the edit distance would be 1 here. Now, whenever you do a DP problem, especially like 2-dimensional, it's always good to kind of familiarize yourself and try and solve like really small, simple cases of it by hand, so you kind of get an idea of the process of solving. So in this case, we can see that if the first string and the second string share several parts, we don't have to replace those, right? We don't have to remove them because they're already done for us. And the only thing that we have to do is replace Y with S. So in this case, changing yang into sang would have an edit distance of 1, right? And but changing yang to code would require an edit distance of 4 because they share nothing in common. And so those are the basics that will hopefully give us some insight into solving the problem as a whole. Now, as always, when it comes to these examples, we will need to, yeah, we are going to need to take an input and follow the implementation process and probably create a 2D list. So let's get coding up on here. So we're gonna have to take on input. So we'll just say let equals input. I mean, yeah, we could name these string 1 and string 2, but I'll just name them myself because I'll also be able to give you guys some examples of, fairly good variable names, let as in letter, tar as in target. So this kind of lets you know what's going on. And it won't be too confusing if you look at the code later on. All right, and now we just need to create the 2D grid. So I usually like to call the grid GR as in grid, or even graph. And this will be for later on. The next lesson will cover graph theory, and that will involve GR, right? So I put in another pair of brackets in order to show that I'm working on the secondary list, and we'll do -1 for k in. And then here we can decide whether or not we do the length of let or the length of tar, but I'll use the length of let over here, as in the length of the original letter that you'll be changing. And we do the +1 here because, well, it will become apparent later on, but we're creating a grid, right? And usually with these 2D DP problems, we want to have a grid that has like at least an extra space. And now we just follow the rest of the, grid creation process or the list comprehension thing. And easily enough, we do for j in range length of tar +1. Okay, so we finished with the 2D list. Now keep in mind here, K and J have to be different. I mean, they don't have to, but if you don't change them, then it's going to be really strange because then you'll be using like this value twice, and that can make it not work properly. So yeah, you want to keep these two distinct. And then, okay, I'll just quickly check the chat. Okay. Oh, the creepy voice thing. Yeah. Sorry, then it's probably control or option or command plus F5. Yeah, because like I think if you do function F5, it gives you like the voiceover or something like that in a like kind of, yeah, creepy voice. Yeah. Okay. Well, you can also probably do press file and then there should be a run tab or something like that. But I think we'll just continue on here. And we've got the 2D list created. So now we just need to go through and work on the like actual dynamic programming part. Now, dynamic programming, since we're working with the 2D list, we'll probably need a 2D loop or a nested for loop in this case. And this will allow us to access all the different values inside the list. So once again, since we're trying to access every single value, we will probably need to use length tar +1, right? Because we created an extra spot, and this will come in handy later. All right, we have our 2D list created. And if we think about it, what this will do is, so this is definitely not the 2D list, but that we're creating. However, we can kind of, I don't know, use it to kind of understand what we're doing. So the first for loop, or like the one that's the least indented, the for k in range, that will make us go through all the different secondary lists. So it will make us move up and down. Well, it will make us move from up to down. And then the second one for j in range will make us move left to the right. So if we were to run this code, it would go from here to here to here to here, and then it just do that, that kind of pattern. It would go left to right, and then up to down. So basically the way that we read a book, right? That's the way it will progress. And yeah, and it's important that you match, for K in range up with, okay, well, I mean, in this case, I use I guess it's kind of confusing. So really, it doesn't matter. Like the way I did it before, where I had for K in range here, it doesn't really matter, but I just want to let you guys, more easily visualize the kind of, I guess, similarity. So this part of the list comprehension codes for how many secondary lists there are. And this part of the for loop tells us which of the secondary lists we're onto, right? All right, so now we have that part done. And then this is the part where we have to get kind of the logic of the dynamic programming problem into place. We know that, with the Yang and the code example, that if two things are the same, well, sorry, if they're completely different, then that you will need 4 spaces of edit distance. But first, here, if we print the graph, we can see that it's going to be empty because we haven't done anything to it. So now we just need to add in the first couple of values. So if all right, and now okay, so what I did here was I said that, if either K or J are equal to 0, then the grid will be equal to the max between the two. All right, now we can just import pprint. Yep, and then run. So I don't know, Yang, and then code. And yeah, as you can see, this is what we've done to the 2D list so far. So as you can see, the upper left-hand corner is 0, and that's kind of what we wanted, right? Because we had these ranges go like one more than the actual length, because we want to remember that ranges, they go up to but not including like the number inside of them. So the length of the target number is 4, right? But if we didn't do the length of target plus 1, we'd only go up to 3 over here. And we kind of want to fill in this entire line from 0 to 4, because this is going to represent how many like changes it will be necessary to do on Yang to get it as code. This is going to like not sound particularly like meaningful, but if we continue on, this will make a lot more sense. But yeah, just as you can see, it works, and we needed to have one more so that we can have like the upper right hand corner, and we're basically creating a kind of chart that we're filling in, and this chart will help us do the dynamic programming. And also -1 in this case is a placeholder, but it also shows, because obviously if you have, no matter what kind of target or original letter you get, you're not going to ever have like a negative edit distance, right? That doesn't make any sense. And so that means that if I set the value of the placeholder as -1, I can instantly tell if a value has been reached or been worked with yet. And this is pretty helpful in future or in other dynamic programming questions. Setting it as 0 wouldn't make much sense, because if I had it as 0, then it would, because 0 is a possibility, right? If I want to change Yang into Yang, I don't have to make any edits, and that can be kind of misleading. So having it as -1 tells me if or if not like a certain part of the code has been reached or modified. Right, so now we've created the first if statement, right? If either of them are equal to 0, then yeah. And what this means is if the hypothetical length of something were 0, then obviously it would take So if I wanted to change, for example, just an empty string into the string, hello, that's obviously going to need 5 at, it's going to have an at a distance of 5 because I just have to insert 5 different letters. And this is the case that we're covering. If you have either one of these values is 0, then the edit distance you have is just going to be the maximum difference. And sure, there could be a case where you try and change nothing into nothing, but in that case, it is also going to be, 0, right? Because the max of 0 and 0 is both 0. And yeah, if I want to change yang into a string with nothing, once again, simple. I just delete everything, and that will require an edit distance of 4. And that is the max between the two lengths. So that's what this part of the code means. And then we do for else. So now that we've covered that case, right, we have to cover the rest of the cases. And then in that case, we can have we need another if statement. So if no, sorry. And yeah, in this case, it's very important to keep track of like what iterator you're using, because at first I put K here, and that would be wrong. Because remember, K is going through the length of your target word. J is going through the length of your original or letter word. And the reason why this is important is because if you switch it up and the two words are of different lengths, then you're going to get an out of bounds error eventually. And that can be pretty frustrating to deal with. So always make sure that you're using the right iterator. Since K is in range tar, you know that K is for tar. And the reason why I have -1 here is because you have to remember, we're running through the length of tar plus 1. And if we just kept it as J or just as K, it would also go out of bounds because the index of, say, the word yang would only go up to 3, not 4. And you might think, oh, well, then what happens when it's index 0? Would it become -1? Well, no, because our first if statement took care of that. If it's equal to 0, then we just, it's the case where you have an empty string trying to turn it into a full string. And that's just the length of the full string. That would be the edit distance. So in that case, we have to operate on the graph. So graph at kj be equal to. And now in this case, it all depends on like what the graph represents, right? So if we think about it, if you have a letter, right? Say you're trying to change, once again, yang into sang, right? You know for sure that in order to change, if it were empty and you change it into sang, it would be an edit distance of 4. So in fact, it would be very similar to this piece of code here, right? The grid. And what we're looking for is the case where A and A are the same. Because as you can see here, we're saying, well, what happens if, the letter that we're on in letter is equal to the letter that we're on in tar. So when we're looking through this, what happens if we're at the case where we're finally at the part where these two sections are the same? Well, in that case, you'd do this. So this gives you the kind of diagonal, like it'd be like going from here to here, right? You go to the previous diagonal. And this should become apparent later on. So yeah, we're just going to move on to the else statement. I promise this will make sense later, especially once I give you guys the I created like a chart to kind of show this, and we'll go through that. So we'll just quickly finish the rest. So yeah, otherwise, we're just going to need to do, because yeah, obviously, no matter what, we're working with grkj, it has to be equal to the minimum. And now it's when we look at these cases. So we know we can either insert, remove, or replace. Now, when we remove a letter, right, what happens is, so let's say it was like this, right? If we were to remove the B, right, we'd make it YNG, but that doesn't really solve anything per se. We still have to compare YNG to SANG, and the problem, you've kind of just pushed it on to another stage, but you still have more work left to do. However, well, not however, but if you had this and you try to replace it, right, with A, then it's all done, right? Because we know we no longer have to check, right? Before, if we were to remove B, then we have to check if N is equal to A. But if we replace B with A, then we know for sure that these two are going to be the same. Because when you're doing dynamic programming, you can assume that like you're not going to be kind of foolish and replace something with like an incorrect word. You're always trying to be the most efficient. So you can assume that when you replace a letter, you're going to replace it with the appropriate letter. So in this case, you can assume that you're going to replace the B with A, right? So in that case, that would be like going to the exact previous, to like the previous diagonal of this grid. And the reason why is because doing so, you've basically forced like the letter and the target at that specific index to be the same. And then the other case were the cases that we looked at before. So yeah, these are the cases. And now you have, so this is when you remove something, and this is when you insert something, because inserting and removing are actually kind of similar in this case. Because if I were to say, if it was like this, YBNG, if I were to insert a letter, right, I would, yeah, sure, like, of course I'm going to insert something so that these two words are the same. But inserting something also increases the length of the string that you inserted into, and that means that you still have to end up checking the letters that go later on. So that means that you actually can't just assume that things are going to be like a perfect match, because you still have to check, you know, the next one, right? So if anything, you've kind of like pushed the problem. You've kind of like, I guess, push it on to the future. So you have to work on it later, because now it's like comparing these strings and it's still 4 against 3. So one of these is for inserting, one of these is for removing. All right, we have 10 minutes left. Okay, great. Well, the implementation is almost done here. So yeah, these are the moves. Now, one crucial step, you have to add the +1. Why? Because if it took like a certain number of moves to get from one like part of the code to the other, the extra move is going to cost an extra bit of, I guess, time or distance. And yeah, so you have to +1 in order to make sure that everything is good. Okay, and now finally, we can quickly run our code to see what is going on, right? If we have if we have yang, we have code. Yeah, that is the graph that we've constructed. So we've seen that because of all the stuff that we wrote, it's completely filled in the graph. And the actual answer to these questions, like what is the added distance between yang and code? Well, since this is, you know, like the upper left-hand corner, maybe the answer is at the lower right-hand corner. So in order to access the lower right-hand corner, you just use the two -1s, right? And if I do yang and code, whoops, sorry. They're supposed to be on separate lines, yang and code. Yeah, it will give you 4. Now, of course, you can't just assume that it's the lower right-hand corner, but now I'm just gonna go over the explanation of this kind of grid. So, right, in this example, I'm using kitten and sitting. right? So if we run the code again and we do kitten and we try and turn it into sitting, we have this, which is the exact same as this, right? So once you get the document in your like hack pack or something like that, you guys will be able to, see this nice graph and visual representation. So let's just work with the bigger version. So what does this represent? Well, the first column represents the edit distance between an empty string. So you can almost imagine that there is an empty string here or an empty string here, right? And the idea is that if you want to change an empty string here into k, that would require an edit distance of 1. If you want to change that empty string to ki, it would need an edit distance of 2, and on and on and on. Now, what about s? When you want to change s into k, you need an edit distance of 1. And how does that work? Well, you replace s with k, right? And doing that, we remember that in our code, when you wanted to replace something completely, that was with k minus 1 followed by j minus 1. And that is moving up 1 diagonally, and that's 0. And 0 plus the 1, cost to replace something is 1. And that's why 1 is over here. And of course, if you want to go s into ki, then you just replace the s with k, and then you tack on the I. Tacking on the I is just as simple as, adding 1 cost, and so is the replacement thing. And the reason why like this works is because when you replace something, you are, when you're inserting the I, right? You go one to the previous, because when you know that when you insert something, you're going to insert the correct thing, right? And so you just have to look at the cost to get from s to k, which is 1. Well, if I want to get from s to ki, then the only difference is the extra I on the end. So I just have to insert the I, which is only going to be a cost of 1. So that's why the cost here is 2. And then, on and on and on. So that's why, going from s to kit is 3, because when you insert something, you just look at the previous cost, which was 2, right? To go from s to ki requires 2, because you have to replace s with k, which costs 1, and you have to insert the I. And then to go from that to kit, you just have to add the t. So that's an extra cost of 1 for the inserting, and then on and on and on. And then finally, well, not finally, but next we have s going from si to, what happens if I want to go from si to, a blank string? Well, it's going to cost me 2, because I have to remove both the cost. I have to remove both s, and I have to remove I at the same time. So that's why it's going to cost me 2. And yeah, it's going to cost me 2. So this builds off of the previous knowledge or information that we gained from changing s into nothing, right? If we want to change s into a blank string, well, we knew that it would cost 1, right? And now when we want to change si into a blank string, well, si is just an extra, character. So we just have to remove something else. So it will be the same as the cost of going from s to blank, except, an extra bit of cost for removing the I as well. And that's why it's 2. So this value of 2 is built off of this value of 1. And this value of 1 is built off of this value of 0. And of course, 0 is just the cost to go from blank string to blank string, which requires no change. And this is, in short, what dynamic programming is all about, because you're building off of the previous values. And this is the explanation for the, relatively weird looking program that we've written, because this isn't very intuitive. But if you look at this graph long enough, and if you remember the idea behind it, where like these columns mean going from blank to k, going from blank to n, going from s to k, and on and on and on, you realize that eventually, once you reach the very bottom, you've calculated all the values necessary to go from kitten into sitting. Well, from kitten into sitting. And that's why the value is 3. So we can keep on exploring this, right? And make sure that our interpretation works. think about it. If you try and go from sitting into a blank, well, it's obviously going to cost 7 because you have to remove everything, right? If you want to go from sitting into K, well, it's also going to cost 7. Well, why? K is, one more than a blank. But the thing is, K, you can't just remove it, like everything except for the S, because then you have the extra step of replacing the S with the K, and hence the cost will also be 7. And all of this is built off of the previous values, right? And at any point, when we think about replacing something, that's when we move diagonally backwards. When we think about deleting something, that's moving, to the left. If we think about inserting something, it's moving up and looking at that value. And whenever we move somewhere, we always add 1 to that cost. Yeah, and you might think, right, like 1 and 1, right? How can you add 1 to 1 to get 1? Well, actually, like the list, the way that this is built, we have to remember that we're going through these 2 nested for loops. So we're kind of moving in the reading order. So we're going from like this to this to this. So at some point, one of these values was probably 0. And these values that we see here are just the finalized values. So the final cost needed to go from, SI to kitten is 5, because you need to replace the SI with K, and then you need to add on the TTEN, which is 4. And that's why the overall, which is 3. And that's why overall the cost is 5. And yeah, just the explanation here, like, it's pretty difficult, and I'll be honest, right? Like, I myself, usually I just memorize the actual like algorithm, because this is fairly easy to remember if you know how to look at it, right? You see here that first you subtract 1 from K and J, then you subtract 1 from K, then 1 from J. And yeah, so remembering this type of algorithm will help you solve the edit distance. But the really important thing is to actually understand the logic behind it and why we construct the chart this way. And if you spend enough time looking at this chart, you will see the logic behind it, and you'll realize that when you look at the final element, or the element in the bottom right-hand corner, you will get the solution to the question. Right, so, all right. Gordon said we have 10 minutes left at 5:09. It is 5:19, so our 10 minutes are probably up. So the lesson might have to end soon. So yeah, that is the very end of the document as well. And the document includes this chart. So just to give you guys a final look at the code, I'll probably add this to the document so you guys can have a copy of the code as well. And remember, this is for the edit distance problem. And I will format this using code blocks. Yeah, so the code will be hopefully a bit easier on your eyes, and you'll be able to look at it. So yeah, the process of all dynamic programming problems is, you have to end up creating the 2D list. You have to go through usually the nested for loops, and you have to look at the cases and slowly build them up in like kind of the reading order that we do, left to right, up to down. And yeah, and finally, just a quick remark on the knapsack problems. Knapsack is also strangely a lot like this. And I think you guys can work on that. Now, Dmoj does have a knapsack problem. So I think if you just search, if you go on a Dmoj, right, and you search knapsack, or like just if you type knapsack into your browser, like knapsack problem, you will definitely get some website that will allow you to try and work on these problems. And once again, the form is very similar. the more 2D DP problems you work on, the more you'll realize that you need to create these 2D lists and you need to go through these nested for loops. And yeah, I'll leave that as a challenge for you guys, I guess, because definitely I feel the edit distance problems are kind of the more abstract ones because you're going from, letters to numbers, which is quite a lot of abstract. And yeah, that'll be about it. So I hope you guys learned something from this lesson. This PDF or this file will be made available to you guys later. And yeah, that's the end. Hope you guys enjoy the rest of your 7-week challenge experience. And we do have another lesson on graph theory. I think at maybe 5:30. All right. Thank you everyone on the chat for listening.